and welcome to the session about process control. So why do we need process control? We often want a system or process to behave in a pre-described manner. The term system can refer to almost any technical process or device. For example, the speed control of a car can be considered a system, with input fuel delivery, which is set with the accelerator pedal position, and output speed of the car. Another example would be a pharmaceutical fluid bed dryer, with inputs flow rate of air and temperature of the inlet air, and a system output granule moisture. Even an entire continuous manufacturing line can be considered a system. The CQAs can be seen as the system outputs, and the CPPs are the system inputs. Typically, the system outputs Y should track a given reference R. The reference is the value that we want to reach. In case of the car, the driver wants the car to drive in a certain speed. The automatic speed controller should then select the system input U, in this example fuel delivery. It should set the fuel delivery in such a way that the desired speed is achieved. The computation of the fuel delivery from the reference R and the current speed Y is the task of the controller. How can we achieve such a reference tracking? Well, one attempt would be to know something about the system. For example, to have a system or process model. That model is then used to compute the required input U in order to achieve the desired output Y. Although this idea seems very promising at first glance, it also has some drawbacks. Coming back to the car example. Assume you know exactly how much fuel you need to achieve a speed of 80 km per hour on a flat road. What happens if the road goes up a mountain? Your car will likely not keep the 80 km per hour. You would need to push the accelerator pedal harder to get more fuel to the engine. The inclination of the road is then disturbing your system behavior. In case of a fluid bed dryer, such a disturbance should be a different granule moisture at the beginning of the drying cycle. The curves on the side show the desired granule reference moisture profile in black. The upper red curve shows the granule moisture in case of a wrong initial moisture content. With a wrong initial moisture, the proposed concept would lead to a deviation between output Y and reference R. In this example, it is too high. Another reason for a deviation could be modeling errors, meaning that your system model does not perfectly describe the real process. Such modeling errors would result in a different output profile, as indicated in the blue curve. Both phenomena, disturbances acting on the process and modeling errors, will ultimately result in a non-zero control error. This control error is indicated in the diagram. The control error is the difference between the reference R and system output Y. To overcome that problem, we can use feedback control. But what exactly is feedback control? To create a feedback control loop, we measure the current value of our process output Y. This can be, for example, the granule moisture. We then use that information in the controller to set the corresponding process inputs. If the moisture is too high, the controller knows about it and it can adjust the process inputs accordingly. This will then lead to a decrease in the deviation between the reference and output. The more information the controller has about the system, the better it can adjust the system inputs U. So-called model-based control concepts are used for that purpose. These concepts will be explained in the next video. With that, I'd like to thank you for your attention.